So far we've invented enough programming to do some very complicated things, and you've surely learned a lot about programming at this point. You've learned almost all the most important tricks that usually don't get taught to people until they have a lot of experience. For example, data-directed programming is a major trick. And yesterday you also saw an interpreted language. We did this all in a computer language at this point where there was no assignment statement. And presumably, for those of you who've seen your BASIC or Pascal or whatever, that's usually considered the most important thing. Well, today we're going to do something horrible. We're going to add an assignment statement. And since we can do all these wonderful things without it, why should we add it? An important thing to understand is that today we're going to, first of all, have a rule which is going to always be obeyed, which is the only reason we ever add a feature to our language is because there's a good reason. And the good reason is going to boil down to the ability, you now get an ability to break a problem into pieces that are different sets of pieces than you could have broken it down without that, giving you another means of decomposition. However, let's just start. Let me begin by reviewing the kind of language that we have now. We've been writing what's called functional programs, and functional programs are a kind of encoding of mathematical truths. For example, when we look at the factorial procedure that you see on the slide here, it's basically two clauses. If n is 1, the result is 1. Otherwise, n times factorial n minus 1. That's factorial of n. Well, that is factorial of n. And written down in some other obscure notation that you might have learned in calculus classes, mathematical logic, what you see there is if n equals 1, the result for n factorial is 1. Otherwise, greater than 1, n factorial is n times n minus 1 factorial. True statements. That's the kind of language we've been using. And whenever we have true statements of that sort, there's a kind of a way of understanding how they work, which is that such processes can be evolved by substitution. And so we see on the second slide here that the way we understand the execution implied by those statements arranged in that order is that you do successive substitutions of arguments for formal parameters in the body of a procedure. These all say this is basically a sequence of equalities. Factorial of 4 is 4 times factorial of 3. That is 4 times 3 times factorial of 2, and so on. We're always preserving truth. Now, even though we're talking about true statements, there might be more than one organization of these true statements to describe the computation of a particular function, the computation of the value of a particular function. So, for example, looking at the next one here, here's a way of looking at the sum. If you look at the sum of n and m, okay, and we did this one by a recursive process. It's the increment of the sum of the decrement of n and m. Okay. And of course, there is some piece of mathematical logic here that describes that. It's the increment of the sum of the decrement of n and m. Just like that. So there's nothing particularly magic about that. And of course, if we can also look at an iterative process for a program that involves an iterative process for the same function, these are two things that compute the same answer. And we have equivalent mathematical truths that are arranged there. And just the way you arrange those truths determine the particular process, or the way you choose and arrange them determines the process that's evolved. So we have the flexibility of talking about both the function to be computed and the method by which it's computed. So it's not clear we'd need more. However, today I'm going to do this awful thing. I'm going to introduce this assignment operation. Now, what is this? Well, first of all, there's going to be another kind of statement, if you will, in our programming language called set. And set, things that do things like assignment, I'm going to put exclamation points after. We'll talk about what that means in a second. The exclamation point, again, like question mark, is an arbitrary thing we attach to the symbol, which is the name, has no significance to the system. The only significance is to me and you to alert you that this is an assignment of some sort. But we're going to set a variable to a value. Okay. And what that's going to mean is that there is a time at which something happens. Here's a time. If I have time going this way, this is a time axis. Time progresses by walking down the page. Then an assignment is the first thing we have that produces the difference between a before and an after. All of the other programs that we've written that have no assignments in them, the order in which they were evaluated didn't matter. But assignment is special. It produces a moment in time. So there is a moment before the set occurs, and after, such that after this moment in time, the variable has the value independent of what value it had before. Set changes the value of the variable. Until this moment, we had nothing that changed. So, for example, one of the things we could think of is that the procedures we write for something like factorial are in fact pretty much identical to the function factorial. Factorial of 4, if I write FACT4, independent of what context it's in, and independent of how many times I write it, I always get the same answer. It's always 24. It's a unique map from the argument to the answer. And all the programs we've written so far are like that. However, once I have assignment, that isn't true. So, for example, if I were to define count to be 1, and then I'm going to define also a procedure, a simple procedure called demo, which takes an argument x and does the following operations. It first sets x to x plus 1. My gosh, this looks just like Fortran, right? In a funny syntax. And then add to x count. Oh, I just made a mistake. I want to say set count to 1 plus count. Which is this thing defined here. And set plus x count. Then I can try this procedure. Let's run it. So, suppose I get a prompt, and I say demo of 3. Well, what happens here? The first thing that happens is count is currently 1. Currently, there's a time. I'm talking about time. X gets 3. At this moment, I say, oh yes, count is incremented, so count is 2. 2 plus 3 is 5. So the answer I get out is 5. Then I say demo of, say, 3 again. Okay, and what do I get? Well, now count is 2. It's not 1 anymore because I've incremented it. But now I go through this process. 3 goes into x. Count becomes 1 plus count, so that's 3 now. The sum of those two is 6, so the answer is 6. And what we see is the same expression leads to two different answers depending upon time. So demo is not a function. It does not compute a mathematical function. In fact, you can also see why now, of course, this is the first place where the substitution model isn't going to work. This kills the substitution model dead. You know, with quotation, there were some little problems that a philosopher might notice. okay, with the substitutions, because you have to worry about what deductions you can make when you substitute into quotes, if you're allowed to do that at all. But here the substitution model is dead. Can't do anything at all. Because supposing I wanted to use a substitution model to consider substituting for count. Okay? Well, by gosh, if I substitute for here and here, okay, they're different ones. It's not the same count anymore. I get the wrong answer. A substitution model is a static phenomenon. It describes things that are true, and not things that change. Here we have truths that change. Okay, well, before I give you any understanding of this is very bad. Now we've lost our model of computation. And pretty soon I'm going to have to build you a new model of computation. But let's play with this just now in an informal sense. Of course, what you already see is that when I have something like assignment, the model that we're going to need is different from the model that we had before, in that the variables, those symbols like count or x, are no longer going to refer to the values they have, but rather to some sort of place where the value is stored. We're going to have to think that way for a while. It's going to be a very bad thing and cause a lot of trouble. Okay, so as I said, the very fact that we're inventing this bad thing means that there had better be a good reason for it. Otherwise, it's just a waste of time and a lot of effort. Let's just look at some of it, though, just to play. Supposing we write down the functional version, functional meaning in the old style, okay, of factorial by an iterative process. Factorial of n we're going to iterate of m and I, which says if I is greater than n, then the result is m. Otherwise, it's the result of iterating the product of I and m. So m is going to be the product that I'm accumulating. M is the product. Okay? And the count I'm going to increase by 1. Plus iter else condefine. I'm going to start this up. And these days you should have no trouble reading something like this. What I have here is a product being accumulated and a counter. Okay, I start them up both at 1. I'm going to buzz the counter up. I goes to I plus 1 every time around. But that's only where I'm putting a time on the process. Each of this is just to have truths, true rules. Okay. And m is going to get new values of I and m, I times m each time around. And eventually I is going to be bigger than n, in which case the answer is going to be m. Now I, speaking to you, use time in this. That's just because I know how the computer works. But I didn't have to. This could be a purely mathematical description at this point, because substitution will work for this. But let's say I write down a similar sort of program using the same algorithm, but with assignments. So this is called a functional version. I want to write down an imperative version. Factorial of n. I'm going to create my two variables. Let I initialize itself to 1 and m be initialized to 1, similar. We'll create a loop. Which says cond greater than I n. If I is greater than n, we're done, and the result is m, the product I'm accumulating. Otherwise, I'm going to write down three things to do. I'm going to set M to the product of I and M. Set I to the sum of I and 1. And go around the loop again. Looks very familiar to you Fortran programmers. Else con define. Funny syntax, though. Start the loop up. Okay, and that's the program. Now this program, how do we think about it? Well, let's just say what we're seeing here. There are two local variables, I and M, that have been initialized to 1. Okay. Every time I run the loop, I test to see if I is greater than n, which is the input argument. And if so, the result is the product being accumulated in M. However, if it's not the end of the loop, if I'm not done, then what I'm going to do is change the product to be the result of multiplying I times the current product, which is sort of what we were doing here. Except here I wasn't changing. I was making another copy. Because the substitution model says you copy the body of the procedure with the argument substituted for the formal parameters. Here I'm not worrying about copying. Here I've changed the value of M. I also then change the value of I to I plus 1 and go buzzing around. Seems like it's essentially the same program. But there are some ways of making errors here that didn't exist until today. For example, if I were to do the horrible thing of not being careful in writing my program and interchange those two assignments, the program wouldn't compute the same function. I get a timing error because there's a dependency that M depends upon having the last value of I. If I try and change I first, then I've got the wrong value of I when I multiply by M. It's a bug that wasn't available until this moment, until we introduced something that had time in it. So as I said, first we need a new model of computation, and second we have to have a damn good reason for doing this kind of ugly thing. Are there any questions? Speak loudly. David?
Okay. I'm confused about, we've introduced set now, but we had let before and define before. I'm confused about the difference between the three. Wouldn't define work in the same situation as set if you introduced it?
No, define is intended for setting something once the first time, for making it. Mm-hmm. Okay? In other words, you have never seen me write on a blackboard, okay, two defines in a row whose intention was to change the old value of some variable to a new one.
And is that by convention or?
No, it's intention. Okay? The answer is that, for example, internal to a procedure, two defines in a row are illegal. Two defines in a row of the same variable. Okay? Executing the same define twice. Whether or not a system catches that error is a different question. But I legislate to you that define happens once on anything. Now, indeed, in interactive debugging, we intend that you interacting with your computer will redefine things. And so there's a special exception made for interactive debugging. But define is intended to mean set up something, okay, which will be forever that value after that point. Okay? It's as if all the defines were done at the beginning. In fact, the only legal place to put a define in scheme internal to a procedure is just at the beginning of a lambda expression, okay, which is the beginning of the body of a procedure.
Now,
okay. Now let of course does nothing like either of that. I mean, if you look at what's happening with a let, this happens again exactly once. It sets up a context where I and M have values 1 and 1. That context exists throughout this scope, this region of the program. Okay. However, you don't think of that let as creating as setting I again. It doesn't change it. I never changes because of the let. gets created because of the let. In fact, the let is a very simple idea. Let does nothing more. Let a variable 1 have value 1. Let me write this down a little bit more neatly. That's right. var 1 have the value of expression e1, and variable 2 have the value of the expression e2. In an expression e3 is the same thing as a procedure of var1 and var2 being formal parameters, and e3 being the body, where var1 is bound to the value of e1 and var2 gets the value of e2. So this is in fact a perfectly understandable thing from a substitution point of view. This is really the same expression written in two different ways. In fact, the way the actual system works is this gets translated into this before anything happens.
Okay, I'm still unclear as then what makes the difference between a let and a define. They could
A define is a syntactic sugar whereby essentially a bunch of variables be created by lets and then set up once. Okay, time for the first break, I think. Thank you. Let me get this. 7. How long was that?